I think the biggest trend right now that we're seeing is miniaturization. Some of the biggest challenges, well, one is if you are designing any sort of HMI, human machine interaction, so AR, VR, or HUD, engineers do love Python. You talk to any young engineer right now, and they're learning Python in school. In the healthcare industry, we're seeing things like measurement and measuring optical systems, not only for diagnostics, but for live capturing of cancer detection or something like that. So really, really, really cool stuff. Right now, we're seeing huge speed ups, on NVIDIA A100s, for example, that are, just bonkers, to be honest.
So Fastware Engineering supports engineers working on a wide range of optical challenges. From your perspective, Jim, what are some of the biggest trends driving innovation in optics today?
The biggest trends, I think the biggest trend right now that we're seeing is miniaturization, right? Where we're seeing these technologies, whether it's, camera and image acquisition or directed energy, in, for example, sensors, everybody wants it smaller, lighter. How many cameras do we have on a car now? You walk up to the car, you don't really see, these massive lenses, right, sticking off the edge of the car. So by miniaturizing these down, one, to become more usable, they become, embedded into all these electronics that we have around us. But it's a challenge, right? How do we simulate that? So I think that miniaturization is what's driving a lot of the development we see right now, some of the optical tools.
So obviously we're seeing optics play a critical role in emerging technologies like, as you just said, Jim, autonomous vehicles, AR, VR, and healthcare diagnostics. How have simulation tools evolved to meet these demands?
How they evolved? Yeah, it's a good question. I think that originally optics tools were really centered around just sort of the lens stack and making sure, focal length was right, image quality was somewhat predictable, right? But, I think in the early days, we had some early optimization, right? To try to account for, say, manufacturing tolerances, right? That's something that in optics, you just have to do on day one. But that's kind of the starting point now. That is, all tools, I think, have that capability. So now what we're seeing is optimization from other areas of, say, packaging or manufacturing or environmental, right? So we're seeing this combination of multi-scale, multi-physics optimization so that we know that a lens stack or any sort of optical system is going to operate in its peak performance window across the widest potential ranges.
Mm-hmm. Beyond the traditional optical design, how does Zemax handle multi-physics considerations, like, for example, thermal and structural impacts on optical performance?
Yeah, that's something we've had for quite a while, which is, we call it STOP analysis, which is structural thermal optical performance. And really what it is accounting for the sensitivity of an optical system on heat transfer, on its thermal profile. And it's not just, say, the ambient temperature changing, which it can, right? If we think about a LiDAR system on a car is going to be out there when it's, snowing, and when it's really cold, it's also going to be out there, say in Arizona when it's 115 degrees outside. But also with the miniaturization, we have optics operating in the proximity of heat generating equipment, right? So we have the electronics next to the optics. And so we don't just have to account for the thermal environment, we have to account for a thermal gradient where one lens will be hotter than the other lenses. And so we do that with our STOP analysis. We have a module that is in Zemax where it's called STAR, and we're able to import FEA results. So no matter which FEA tool, whether you use, whether it's ANSYS or not, ultimately you're going to get this deformed, gradient, this deformed lens, right? So my lens goes into FEA, I heat it up, I shrink it down, and I twist it and tilt it and bend it. And that new geometry, that deformed geometry, can get automatically input at full fidelity. And we basically rerun our ray tracing on that new deformed lens, that new deformed curvature, and we can see what the impact is to things like focal length and image quality.
When it comes to lighting in the automotive applications, there's a tool called SPEOS. Can you quickly explain what this is all about?
Yeah, SPEOS is a really, really cool tool. And it is a non-sequential ray tracing tool in a CAD environment. So, a lot, and you mentioned, right, it comes from the auto industry where it was really developed and honed. But, imagine being a designer and designing a lighting system. You are probably responsible for the curvature, the design, the look, but also the optical performance. So we've got this 3D, very interactive CAD-based environment where we can put our lenses in, create our stack, perform our non-sequential ray tracing. We can predict the visualization and a host of post-processing ways to essentially make it a very interactive part of the total design experience. So it's really, really, really cool. Like I said, it kind of came from the auto industry, but really it's being leveraged everywhere, right? We have lighting systems all around us from architectural to high performing stuff.
What would you say, Jim, are the biggest challenges engineers face when designing these systems, and how does SPEOS help solve those?
Yeah, I think some of the biggest challenges, well, one is if you are designing any sort of, human sort of, HMI, human machine interaction, so AR, VR or HUD, right? Heads up display. It's really important that you're able to visualize how the human's going to see it, right? So how is the human, eye, retina, how are we actually going to see it? And, sure, we can use humans for testing, a little subjective sometimes. So we have these sensors that replicate human eyes. We're able to render exactly what we're going to see. And so I think that's really, really, really important, especially as we start to see this growth of, augmented reality, right? So we have smart glasses, and certainly in, I would say, maybe the more extreme environments, right? So aerospace and defense, we've been using a lot of this augmented virtual reality heads-up display for quite some time. And it's really, really important to understand how the pilot sees things, how the driver sees things, how the consumer sees things. So that's one really big thing. I think the other thing that SPEOS does really well is optimization, right? So as I mentioned before, all optical systems have to be optimized across physics. And SPEOS has a lot of different ways to do that, to account for not just geometry and optical variability.
Yeah, that makes sense. You mentioned non-sequential ray tracing, allowing for complex light interactions. How does SPEOS handle real-world issues like stray light interactions or analysis?
That's a good question. Traditionally, I should say, or in some cases, you've got this optical designer over here, you've got this mechanical packaging designer sort of over here, right? And those are separate people. And so we see, unfortunately, sometimes this silo of roles in the organization. And I think sometimes, right, tools can help sort of remove those communication barriers. And an example would be, I think stray light analysis in SPEOS. We have to have an understanding and characterization of the optical part of the system, and we also have to have the packaging around it. That's really what stray light's all about, right? Is how am I going to design an enclosure, right, that goes around this system? And if it's a system that's very, very sensitive to any sort of stray light, then we need to account for manufacturing tolerances of the system, of the packaging, and so since we're in a CAD environment, we already have that, right? We already have all the 3D geometry from the packaging. It's not just optical lenses in our analysis, it's all the other things around it.
As we all know, engineers love Python, right? So how can we integrate SPEOS in kind of the modern engineering workflow for advanced scripting and optimization? Can you maybe share some anecdotes and maybe examples of how we can unlock new possibilities of engineering?
Yeah, I mean, engineers do love Python. You talk to any young engineer right now, and they're learning Python in school, right? That's a little bit, I'm a little too old for that, I guess. So I've got my Python book. I've read about 2 pages of it, but certainly we're able to access a handful of different physics libraries and other ways to kind of wrap, if you will, some scripting and some automation and some intelligence around the core physics, right? So, most engineering tools nowadays, most engineering simulation tools have an API for Python so that you can hook in to any, say, business, bespoke, intellectual property driven optimizers. But we've got a connection in, we can optimize at the geometry level. We can optimize at the system, the optical system level. We can optimize because it's CAD based. We can go to the higher system level, and we can even go down to, say, the texture level, right? So, as we see this trend in miniaturization, we're starting to see the use, the engineering design of some very, very small surface textures, and we can get some sort of macro effects. And we want to be able to optimize on all those scales, right? Nano, micro, macro system, et cetera. And having a tool that's scalable like that, but also hooks into Python in case you have some specific requirements that need to be optimized at those levels is really, really, really important.
Now we have a different tool, Jim, which is Lumerical. So how does that help engineers in terms of photonics and optical sensors?
Yeah, it's a great question. So I guess the third sort of head of the dragon here in our optical offering is Lumerical, and that's really down at the photonic level, right? That's at the sensor level. And a lot of optical designers and optical packaging, engineers, maybe they just purchase the sensor. Maybe they just get something off the shelf, or maybe they partner with a supplier to actually do that. But again, with miniaturization, we're cramming so many things in such a small space. We're seeing optical companies want to have control over the sensor, right? There's a big trend in semiconductor right now to have bespoke dies, right? Bespoke silicon, if you will. So, people, you're responsible for your end product, and that, as you look at quality up the supply chain, goes all the way up to the smallest part of it. And in optics, that comes to the sensor level. And so, Lumerical helps design and account for, again, thermal and electrical noises, signal to noise ratio, and designing some of the small intricacies at the photonic level, the texture, the performance, et cetera.
Yeah, can you talk a little bit about cutting edge applications? Because as you said, it operates at the micro and nano level. Maybe we can have some applications to talk about.
Absolutely, yeah. I mean, I think one of the big, one of the big trends again in the industry is what we call co-packaged optics. Again, where optics are combined with the whole system, right? Electronics. We're seeing that at the data center application. We're seeing that in as we move towards quantum, right? We have these photonic integrated circuits, these photonic ICs, and we need to have tools that can transcend the nano to the micro. I mean, every industry right now is innovating at this sort of scale, right? At this measurement scale, aerospace and defense, automotive, communications, et cetera, right? So optical cables, et cetera. Healthcare is a big one too. We have a lot of new sort of medical startups, right? What a great time to be in the healthcare space with an idea, right? We've never had more access to tools and to capital, right? So in the healthcare industry, we're seeing things like measurement and measuring optical systems, not only for diagnostics, but for live capturing of, say, cancer detection or something like that. So really, really, really cool stuff.
You mentioned quantum computing. We have LiDAR and also biomedical imaging. So how does Lumerical support the development of high-performance optical sensors?
Yeah, I think that it comes down to balancing the optical performance, at the chip level as well as the system level, right? So we want to make sure that, at the chip level, we're efficient thermally, right? That we're packaged properly for manufacturing, right? And also that will translate up the scale, right? Up to, say, the board level, up to the optical level, et cetera. So, I think that it's really important that we're leveraging tools that can communicate across, the distance scale, right? From nano to micro to macro.
Mm-hmm. Now, as we all know, GPU-accelerated solvers are enabling faster, more complex photonic simulations. So how does this technology impact the scalability of photonic design?
Yeah, it's a great question. I mean, we have, at Lumerical, we have a finite difference time domain solver, FDTD, that leverages multi-GPUs from NVIDIA, right? So, and we've talked about this before, right? If you're innovating in the simulation space, you need to be providing a tool that can facilitate a 10x in complexity, I think. So how are we making sure that as components, as things that we design, and again, in the optical space, we're thinking about, at the micro to the nano scale with meta lenses, with textures, right? How can we how can we simulate something that's 10x? And the answer isn't just apply 10 times more, money at the problem or 10 times more computing at the problem per se. It's how do we develop the software so we can leverage the technology of today's GPUs, tomorrow's GPUs, and whatever technology, right, quantum comes after that. So right now we're seeing huge speed ups, on NVIDIA A100s, for example, that are, just bonkers, to be honest.
With optics becoming more interdisciplinary, so spanning electronics, material science, and AI-driven design, how do you see the role of optical simulation evolving maybe in the next 3 to 5 years? What do you think, Jim?
That's a great question. I think one of the things that we need to think about, right, is IP protection, right? We need to be thinking about as system companies, right, as product companies are developing and optimizing their optical system all the way down to the chip, they also want to protect that. And so, there's some ways that we can do that, obviously, with a full security protocol for a company, but also at the software level. So our software tools have the ability to compile and protect some of this information. We have to share it in some cases with our customers or with our partners or suppliers, depending on how we're developing these systems, but we need to be able to protect that. And so I think that's kind of a key role. There's a huge conversation right now, of course, as we continue to develop more chip-based, technologies, right, that we protect ourselves. And so I think that's important for engineers to do. I think it's important for the tools to facilitate. And of course, optimization, right? Of course, how are we able to use a tool to bring in, algorithms, right, that can optimize using math and statistics and AI and ML on a way that the human designer just can't do. So those are two, I think, pretty important things that we need to consider moving forward.
I'd be interested, Jim, from your perspective, for engineers looking a little bit deeper into optics and all the tools that we mentioned, what advice do you have for them or any resources that you would recommend to kind of expand their knowledge on this topic?
Yeah, I mean, I think that, there's a lot of people that are interested in optical system design. And there are not a lot of people that call themselves optical engineers, right? There's a handful of, say, college programs that you can go to that are formal, right? University of Rochester, Arizona State, Rose-Hulman, right? I think UCF down in Florida. So, there's a couple of schools that have these very, very good programs. But I know a lot of people who are in the optical space that just kind of fell into it, right? I kind of fell into it, to be honest. It was never on my radar. I'm a mechanical engineer, and I just happened to, in the early part of my career, work in aerospace and defense and kind of sit next to all the Zemax users. So, you learn that multi-physics sort of dependency, right, between the chip, the lens, and the system. So I think that if you are interested to learn more and you're on your way into college, you could look at those programs. If you're interested to learn more, you're looking for resources, obviously there's a whole host of resources around using these tools, whether it's the help files or tutorials. But as far as like simple packaging goes, this is my go-to, the field guide on optomechanical analysis. And like, there's a couple of, these are just classic design examples, right, of how to secure lenses, how to design something that is, going to withstand manufacturing tolerances and potentially structural thermal considerations. And these are just guidelines, right? So this is a great starting point, right? So, clean room classification, right? So these are just simple guidelines. It's a great resource. I know it's paper. Some people like the digital, so I'm sure there's a PDF somewhere out there, but I think there's a lot of resources available. And I'll say this, it's a really tight-knit community, which is awesome. I recently got a chance to spend a couple of days with the Zemax, product team and the tech support team and the whole optical team at ANSYS. And it was such a great experience to just learn from each other. It feels to me like the early days of FEA, when we were doing some really, really innovative stuff. It really wasn't, sort of democratized yet. And so I kind of feel like we're right there with optics. We're really on the tipping point of kind of democratizing some of the knowledge, which is super exciting.
Excellent. Thanks a lot, Jim.
Yeah, thanks, Yusuf. Appreciate it.